This is Software Engineering Radio, the podcast for professional developers on the web at se-radio.net. SE Radio is brought to you by the IEEE Computer Society and by IEEE Software Magazine. Online at computer.org/software.
Hello, this is Adam Gordon-Bell for Software Engineering Radio. Today, I'm speaking with Jonathan Boccara, author of The Legacy Code Programmer's Toolbox. Jonathan has been a C++ developer for 8 years. His focus is on writing expressive code and working with legacy code. Welcome to Software Engineering Radio, Jonathan.
Thanks for having me.
So today, we will be talking about skills for working with legacy code. We have a previous episode, number 295, with Michael Feathers that also touches on this subject. But let's start with some definitions. So can you define legacy code?
Right. There are, I think, several definitions out there, but all have in common that thing that it's a negative thing. It's essentially existing code that's hard to work with. So that's essentially the gist of it. Now, since I wrote a book on how to work with legacy code, I had to come up with a more precise definition. So my definition would be threefold. First, it's code that's hard to understand for you. Second, it's code that you're not comfortable changing. And three, it's code that you're somehow concerned with. So that's my definition. I try to define it as close as possible to something like of the colloquial term that people use in the day-to-day life, legacy code. Now there are other definitions out there, like for example Michael Feathers, which we just mentioned. Michael defines legacy code as code without tests, and some people have other definitions. Some vague definitions include like the code that was there before I got in my company, for example. That's something we can hear. So yeah, it's all around the same theme, really. It's code that's existing, that's already there, and that you have to work with, and that's not easy to work with.
I think that matches my intuition of what I think people mean when they say legacy code.
Mm-hmm.
So in terms of Michael's definition with tests, do you feel that there's cases where that doesn't fit, where code has tests and still is legacy code, or vice versa?
Well, I think it's a pretty good definition, of course. Although, I think there are some cases where there are tests, but it would be still hard to understand, like when you actually get into the code that is tested, or that you wouldn't be so much comfortable changing because of how it's written. And when we talk about tests, I think this definition of test means unit tests, which are automatic tests. Like it's code that is testing some other code. So you write that kind of code and you run it often, so that you've got a quick feedback and regular feedback about whether or not you broke something. So that's a unit test. But when you write unit tests, you have to write enough tests to have enough coverage to be confident with your legacy code and be more comfortable changing. So I guess you have some code that has some tests, or some tests that are not relevant, and you wouldn't be so comfortable changing it.
How much legacy code do you think is out there?
Oh, I think quite a lot, like millions and millions of lines of code for sure. Legacy code is everywhere. I don't think I've met anyone who doesn't have to deal with legacy code in a substantial portion of his work, at least from what I remember. I think the people that don't have to deal with legacy code are perhaps students or people that do programming as a hobby. In that case, you are in full control. You probably wrote all or most of the code, and there's not so much to do with that at the same time, so it's still manageable. So for students and hobbyists, I guess that would be close to 0%. But for professional developers, it's everywhere. I don't know, perhaps, like 95%, just for the sake of not saying 100%. But it's like, very, very substantial bit. That would be my rough estimate.
So in your experience, you mentioned, students would be people who might not interact with it. Is coming to terms with dealing with legacy code an important skill that developers have to build as they enter the professional world?
Yeah, it's like it's a crucial skill to have. When you think about it, when you get into a new job, like it's like your first job or something, you're probably going to get into an existing project, and perhaps this project or company has been there for years, and some other people have worked on it, perhaps quite a lot of other people, and so on your first day, you're going to be thrown into that huge sea of code written by perhaps dozens or more of people over years. So you have to be able to work with that somehow. It's funny because I was browsing through the episodes of SE Radio. There's one that I haven't had time to catch up with, which is by Adam Barr, which you interviewed about bad code. And Adam has written a book. It's called The Problem with Software: Why Smart Engineers Write Bad Code. I haven't read the book yet and haven't listened to, I've just listened to the beginning of the interview. And my impression of what Adam is saying is that we as a community, even though there are some very smart people, tend to write code that's not so good. So when you enter a company, chances are you're going to have to face some code that's not as easy to work with as you would wish it were. So yeah, that's an essential thing because that's what's out there, and you have to do something with it.
Yeah, it is a great interview, by the way. I listened to it, and it's really informative. If we're in this role, how do we develop an understanding of a legacy code base that we're thrown into?
There are quite a few ways, I think, to understand legacy code. I think there are a few different scales, really. It would be interesting to have a global overview, knowing where is what, and also being able to read code like you would read English, So that I think these are the two scales we want to develop. There are quite a few ways to do each one. I talk a lot about that in my book. But if we can pick a few for each, if that answers the question, let's say for having a global view, you can rely on call stacks. Like a call stack is some sort of like slice of a program, of a running program. A program is essentially composed of function calling other functions or calling objects methods, and sometimes a function calls another function that calls another function, and so on and so forth. And in big code basis, that could be quite a few layers, and all piled up that forms a stack, and that's called a call stack. So what I'm saying is that it's interesting to read stacks. Like you pick a stack in your running program and see what's in there. Now there are, I don't know, like perhaps an infinity or not that much, but like a ridiculous amount of stacks you can look at in a program. So have to know how to choose your core stacks. A good core stack, an informative core stack, in my opinion, is a core stack that's both deep, that means that's high as a stack, and in a typical use case of the application. Now, how do you find such a core stack? I mean, a deep one and a one that with a typical use case. Well, the thing to do is to find a typical use case, and finding a typical use case. Well, that's something that's easier to do. Like you can ask the business people, like they can, or clients, if you have access to them, ask them what they do, like what they like doing with your application, and you'll have your typical use case. Or worse, come to us, you can look at the documentation, saying what are some things your application's doing. Like you can find use case probably easier than you can find somebody who's knowledgeable about the code. So that would be to have like one technique to have a global view and starting to see how big chunks of code interact with each other.
So you would find a typical use case and put a breakpoint in there somewhere, and then you're looking through the call stack. And so the idea is that this will give you an idea of how things are called at a high level.
That's right. And that would be a typical use case, and preferably a deep one, so that you can see a lot of layers.
So this gives a high level view of things. Is there a point at which we should start digging into the actual code?
Yeah, at some point you'd have to. Anyway, I mean, our job is working with code, so at some point you have to read code. I mean, reading code is what we do really most of our time as software developers. So yeah, sooner than later, you have to read some code, and you're presented with that piece of text, really, source code, and you have to make some sense out of it. And sometimes you have to read quite a lot of code because like you're searching on something, for example, or you're trying to figure out like this massive function or big object or several functions that work together or whatever. So you have to read codes. And if you want to be able to produce anything in a reasonable time and keeping the thing interesting and not boring, you have to be able to read code fast. And reading fast is a skill. It's not magic. It's not reserved to like an elite or something. It's a skill, and anyone can have it. Reading code fast. And in my book, I take inspiration from how to read a book fast, like prose. There are techniques to be a fast reader of a book, or to be like a speed reader. And one of them is, for example, to go for the places that tend to contain the information. In a book, it happens that the information is at the beginning and at the end, most of it, like the gist of it. And that's apparently true for most books, and that's also true within a book. Like in a given chapter, at the beginning you have like an overview, at the end you have like another overview, and that's where you can get most of the information, and the rest is more like details. And that's true for a section, that's true for a paragraph, and apparently that's true in a book. And I think that's also true for code. And I think that good places to look for information is at the beginning and at the end. And the beginning is something that's quite natural to read, because like you tend to start with the beginning. Like you want to figure out what this function is doing, and you start reading it from the beginning. So yeah, that's something that's quite natural. What I say is that reading the end is also interesting, and I advocate that you should start by reading the end.
What's the advantage of starting reading a function from the end?
Well, when you think about it, the purpose of function is to do something. Like actually doing something, like performing an effect, or it can be computing something and returning it. So the function is written for something, and all the body of the function is typically oriented towards producing that goal. And that goal is likely towards the end. Like, for example, if your function has a classical pattern of returning something, and the last line of your function is return whatever, then you know by reading the last line that all the purpose of that function is to return that thing.
So for instance, if you look at the end and see that it returns like a file descriptor, then you would be able to read it knowing that it has something to do with figuring out what file to return. Is that the idea?
Precisely. And in more convoluted cases where a function has several exit points, like several return statements, the idea would be to read them and try to have a feeling for what they have in common. So that would indicate what this function is returning. And the end of a function, in most cases, that's the end of its source code. But in some cases, which are more complicated, the end of the function is not at the end of the code. The end of a function is more like the output of the function. And I think that's what you want to figure out. And it can be returning, or it can be like, you can pass an output parameter to the function, which is like a variable. You pass it so that the function sets its result into. So that counts as a quote end. Or if the function performs a side effect, then that counts as an output too. So that's what you want to look at first.
In your book, one thing I found interesting was you had some techniques for dealing with functions that were very large. So if I wanted to understand a function that just wouldn't fit on a screen of my monitor because it's quite long, how might I tackle that?
Right, it is a real issue. Like there are functions, like a monitor has typically, 50, 100 lines, max, even less than that. And there are functions that are several hundreds of lines and even several thousands of lines. And you hear of those myths of like functions that are like tens of thousands of lines. But that exists. You do have long functions, and if that function can't fit on a screen, then you can't look at it as a whole, and then you have to fit some of it in your head while you're reading the rest of it, and that can be a challenge. So that's a great question. Well, Yeah, there are quite a few ways to tackle that one. Well, first, you can start by reading the end, like we were saying before. Now, if it's so big, it may be doing several things. So the end might be just one of those. So there's one technique I found. Like one day, a junior developer asked me like how I could read code fast, and when you gain experience, you just read code faster and faster, and you don't always realize how you do that. So I tried to try to realize what exactly I was doing, like what subconscious reflex I had allowed me to figure out a piece of code. And I found that I was looking for words that came up frequently, even if in just like a few lines of code or in like hundreds of lines of code. I think that's an interesting indicator. So imagine for the sake of the thought experiment that you're reading just 10 lines of code and say that it's code that's not immediate to figure out. And trust me, there are some 10 lines of code that you can't figure out in just a second. Then what you want to know is, what is this code about? Like perhaps you have no idea what it's about, what it is purpose, what it is doing. If you find a term, just a term that could be the name of an object or a term that comes often in the function that are called in that piece of code, then you have it's a clue about what it's about, right? And if you know what it's about, then you can have this hypothesis about what it's about. And if that hypothesis happens to be true, and often it happens to be true, then all the rest clicks into place, and it suddenly makes sense. And that's how you can figure out that quite quickly. Now, it's easy to do for a handful of lines because you can have them within your site. But if you have this vast function of, I don't know, say 2,000 lines, for example, there's no way, for me, there's no way I can scan it and scroll down on and remember what words I've seen and trying to figure out which one I've seen most more than others. So I think you can make this analysis more systematic by using a program that would count the words of your code for you, that would make a report of the most frequent words and how frequent they were in a given piece of code. So if you feed a function to that program, it will tell you what the stars of that functions are, if you know what I mean. And if you feed it a file, it will tell you this file is mostly about such and such concepts. And knowing what a file is about is really useful. So that would be how I would approach a long function if I can't modify it.
So it's almost like making an index, right? Like the index of a book, you're saying.
Yeah, exactly. But in sorted order.
Oh, because the frequency is the important thing.
Right. Yeah. Now, I think there are at least two things that are interesting to monitor. One is the frequency. So you want to sort them by descending order. And another measure I found interesting is the span of a word. By span, I mean that's not a term I invented. It's a common term in programming. It's the distance between the first occurrence and the last occurrence of that term. Distance in terms of lines of code. If you see a word that comes up frequently and that has a small span, that means that there's a region, a local portion of your function that's intensive with that term. And that's interesting to know because that will mean that this portion of the function is you can mentally represent that. It's like a sub-function. It's like a sub-part of your function. And that helps mapping out what a function does by having these small regions that are focused about one specific thing.
Yeah, it's like a refactoring opportunity almost.
Exactly. Yeah, that's a refactoring opportunity. Actually, this kind of program, I could test out this kind of program because I wrote one, and if like a listener is interested to run their code with, you can find one on fluentcpp.com/word-count. Maybe you can include that in the show notes.
Definitely. So another thing that's in your book, you advocate for developing an ability to critique legacy code in depth, to have specific feedback about what's wrong with it. Why is that a useful skill?
It's a useful skill. It's a very useful skill, and I'm going to explain why. But it's also a dangerous skill, I think. Well, let's start with explaining why it's useful. When you look at a piece of code that you have written a while ago or that someone else has written, something that's not fresh for you, it happens. And if you're a software developer, you know that it happens, that it doesn't look quite right to you. Like it feels like it's badly written. And when you see that, you have two choices, I think. One of them is saying, this is bad code, and move on. And the second choice is to try to express why this is bad code. Because it happens that you know this piece of code is not well designed, but you can't quite place your finger on what exactly is wrong with it. And sometimes it takes a bit of time of reflection and analysis to exactly pinpoint what's wrong with that piece of code. And being able to critique this code in depth, by in depth I mean being able to voice exactly in excruciating details why you don't like it. Once you find that, when you identify what's wrong with it, you know what to pay attention to. You know that specific aspect of design. You know it's important because it made you feel uncomfortable in the first place. And next time you're going to write your own code, then you know you need to pay attention to that. So by doing this kind of analysis, you get better as a programmer. I often compare that with a vaccine. Vaccine in like a medical vaccine where you get a shot of a disease, but that's not dangerous, and your body has time to analyze it, and do its stuff with the immune system, with antibodies or whatever, and then your body remembers it. It remembers exactly what's wrong with that molecule or whatever. And if you happen to actually encounter the actual disease, then your body is going to recognize it and smash it apart in no time. And I think that analogy is fine for bad code as well, because if you spend time to analyze why bad code is bad, then you won't write bad code for that particular aspect, and will recognize it easily. Now, yeah, I was going to say it's also a dangerous thing to do, to critique, or rather to criticize code, because like going back to legacy code, that's something that people don't like. I mean, as a natural reaction, people don't like existing code that they feel is badly designed. And sometimes it's badly designed, sometimes it's not badly designed, and it's more difficult than it looks, but it's not really the point. An important message I'm trying to get across in my book, in my blog, or everywhere, is that you should not complain if you don't intend to improve the code. So you don't criticize just for the sake of it, because it's a natural thing to do. And if you start by saying, "Oh, this code is terrible. Oh, I would have done such a better job," and you do that all day, then you're going to get depressed, and you're going to depress everyone who sits around you. So I think you need to be careful to criticize only for learning purposes or improving the code.
You feel that there's a proper attitude that people should bring to working on legacy code?
I think so, yes. I was lucky to learn that very early on in my career, and I try to repeat that to every person I have in my team, and every time I can, really. If you have to work with code, be it good, be it bad, be it the one you wrote, or be it the one that someone else wrote, think about it as your code. If you're working on it, this is your code. You have to take ownership. And even if you don't think it's good, even if you didn't write it yourself, this is your code. And when you get into that mindset, you have the position as a leader. You feel empowered to do things with this code because this is your code. So it doesn't matter that it's bad. You have to make the most of it. And when you take the ownership over the code you're working on, you leave this victim attitude, feeling that's one thing that's particularly frustrating with legacy code. It's when you feel like you're bearing the consequences of someone who made a poor design in the past.
Mm-hmm.
And it's not true, because, well, in the first place, maybe that person didn't make a poor design. Maybe just not seeing the big picture, and maybe even in the same situation, you wouldn't have done such a better job. But more importantly, yeah, it empowers you to do great things, and you can do fantastic things with legacy code.
So if we approach it with the right attitude, and we are going to make a change to some code, and so we come up with a useful critique of it. Actually, what are some examples of something that you would consider like a useful critique of code as opposed to just having the wrong attitude?
Oh, that would be any critique that's technical. And once again, for the sake of improving the code or for the sake of your learning, one thing that comes up very often is levels of abstraction. I think that's like the main thing in programming. If I had to sum up best practices in 3 words, that would be those levels of abstraction. That's something that's sometimes not respected, and that makes the code look bad and complicated. I'm just going to quickly describe what I mean by a level of abstraction. So if we go back to our example of a call stack, we've got functions, calling functions. If you look at a particular layer in that stack, that defines a level of abstraction. A level of abstraction is defined by what you're doing. And to go down to a lower level of abstraction, that corresponds to the question, how are you doing it? And that would be one step deeper, or deeper is a bit ambiguous, but towards the top of the core stack. That's the lower level of abstraction. And when you have, so that's easy to see with the core stack, but it's everywhere in programming. Like if you have a class, then the interface is a given level of abstraction because this is what the class is doing, and the implementation of the methods is a lower level because it's how the class is doing what it's doing, and it's absolutely everywhere. So sometimes you have some low level code that explains how it's doing stuff, that's in a place where it should mention what it is doing, and that's why offloading code to sub-functions is so useful, because you can replace a chunk of code with just a label. So that's just one kind of thing you can notice in a piece of code, and that's like one of the first things you get to notice. Now, when you get more and more in depth, you can notice very smaller things, say like the names of your parameters, for example, in the function that don't respect the correct level of abstraction. Because, for example, they have names that resemble something that's inside the function. Inside of the function is instead of what the function is doing as a whole, like how this parameter participates to what the function is doing from the point of view of somebody that calls it.
So you were saying a mistake people could make is having the parameters named incorrectly. Could you explain that?
Sure. So when you have to choose a name of a parameter or anything else really, but let's stick to the parameters example. That's a tricky thing to do. That's like naming is a difficult thing to get right in programming, surprisingly. I think that to get the right name, you have to choose the name that's at the right level of abstraction. And to do that in practice, you have to think about what this object you're trying to name represents. It may sound a bit trivial, but this question, what is this object representing, I think it's the crux of how to do good naming. For the example of the parameter, if you name your parameter with a name that reflects how it participates to the inside of the function, then you're too low in terms of levels of abstraction, because the parameter represents something that's at the same level as the name of the function, how it participates to this function, how it must sound like something logical to pass to the function. If it looks like something that's logical to implement a function, then it's too low. And on the other hand, if you're too high in terms of level of abstraction for a parameter, that your parameter is bound to the context of the function, the context that uses that function. And that's a natural thing to do, because sometimes you're creating a function just for the purpose of using it in one place. So the only example of naming you have is the surrounding naming surrounding the core site. Now, the second time you're going to use that function, you're going to look at its interface, and sometimes it's not going to fit with the new context. And when this happens, you know that the parameter has a name that's too high in terms of abstraction because it's connected with the other context. And then I think a good thing to do in that case is to go back to your parameter, think about a better name that would fit for both contexts, and then you'd have something that's closer to the level of abstraction of the interface. Does this make sense?
I think I understand. So I'm thinking of if I have some function that is called, let's say, format email, and it takes in a string and it goes through and it removes any like double line breaks, right? And I call it that because I use it to format my email. So that is kind of a violation of this levels, right? Because it doesn't actually format an email. I'm giving it too specific of a name. What it's actually should be called is something like remove extra line breaks.
Exactly. And your parameter shouldn't be called email, but should be called text, for example. And that's an example that's a great example because it shows immediately. But there are more tricky ones that you see in day-to-day code and that are not so well defined, and you have to think hard about them, you know?
Yeah.
DigitalOcean is the easiest cloud platform to deploy, manage, and scale applications of any size, removing infrastructure friction and providing predictability so developers and their teams can deploy faster and focus on building software that customers love. With thousands of in-depth tutorials and an active community, we provide the support you need. DigitalOcean stands out of the crowd due to its simplicity and high performance with no billing surprises. Try DigitalOcean for free by getting a $100 infrastructure credit at do.co/SERadio.
So one thing I was thinking about reading your book, if we need to learn to develop skills at finding what's wrong with legacy code, but yet you're saying 95% of code is legacy, like where do we see better code? Where do we learn what good code looks like?
Well, there are a few places you can read good code, and if you do read good code, you're going to develop an unconscious model for good patterns. And when you're going to read your legacy code, some things are going to jump out to you because they are not going to match the patterns you've learned by reading good code. It's like reading good English. Like if you read good English often, then your written English is going to improve. So where do you find good code? Well, one example is to read code that uses the standard library of your language. The standard library that's shipped with the language typically helps you accomplish things with concise code. That's a great way to improve, to raise levels of abstraction, really. So reading code that uses your standard library is a good example. Now, where can you find such code? Well, I think you have several places. One of them is like on the internet. You've got like blogs, for example, that teach you how to use your standard library with code examples, and you can like see the pattern. If like for the sake of C++, for example, I don't know how many C++ developers are out there today, but like if you go on fluencypp.com/stl, you see like a collection of articles showing how to use the standard library. Now, you can also look for standard library usages in your code base, for example. And when you stumble upon them, try and think if you like that code. And if you do like that code, that's a good example. Now, going a bit like more generic than the standard library, you can read code that uses libraries in general. There are some languages have some canonical libraries that extend the language and like push it forward and do amazing things with them. Like another C++ example, I'm sorry, I'm a bit C++ oriented, but in C++ that would be Boost, for example. If you're a C++ developer, you probably know what Boost is, and if you don't know, just go and boost.org and you know everything about it. And Boost pushes the language forward and does amazing things. And if you go and Boost documentation or on Boost books, for example, if you're interested, I can give you some references you can put in the show note. You'll see what things you can do with C++ that you never dreamed about doing. So that would be new patterns that you'll see and that you can use in your interfaces. Other places you can read, you can try and get some info about what's coming up in your language.
Before we leave Boost, so do you have an example of something that you have learned that has helped your work with legacy code that you've learned from Boost?
Well, yeah, one of my favorite Boost libraries is the ranges. And so the ranges is a bit like if you're a Java developer, I think that's a new thing, what happened a few years ago, that's called streams. And I think a lot of languages have that. Python has that, but I can't remember the name. So it's about performing operations on collections and chaining up these operations. Like you've got your collection and you send that to some sort of component that would apply a function to every element of your collection. And you send the result of that to another component that will filter, for example, on a predicate. And you send that to a third component that would do another basic thing. And all put together, you can have like a modular toolbox to do operations on your collections. And the code that uses that is absolutely beautiful. And actually, this went a bit further in C++ because there was a famous library that went further than that, which is called range v3, and it will be in C++ 20. And this, I learned it in Boost for a start, and I use that in my code, and wow, that really makes a difference, be that in legacy code or in your hobby code even, to handle collections.
So because of that, you're able to take the legacy code and use some of those techniques, which makes it easier to understand or change?
Absolutely, yeah.
So that's an example, right, of going into some legacy code and improving it. So should we just, jump in and improve things whenever we get the chance when we're working in a legacy code base?
Oh, no, absolutely not. I don't think so. The thing is, it would be great in theory. If you could fix the world, that would be awesome. But the thing is, legacy code base tend to be vast. Like, one thing that makes code go into legacy code is age. Like if you have old code, it has more chances to be legacy than like brand new code you just shipped.
Mm-hmm.
It doesn't mean that every old piece of code is legacy, but there's this trend of old projects that have code that's difficult to work with. And if a project has time to grow old, then it has had time to grow big. So a legacy code base can be vast, really. And in a vast code base, there are a million things that could be improved. So I think there's no way you can fix everything and make every last line of code absolutely perfect in your legacy code base. So I think that's something you need to realize, and it's okay, and it's a great thing that it's okay. And I think one way to see that is the 80-20 rule. I don't know if you know what I'm referring to, but that's this proportion, this proportion that seems to be there in pretty much every domain. I think it originated in economics with Pareto's observing that in a society, 20% of the people held 80% of the wealth. And this 20-80 can be generalized in 20% of the causes trigger 80% of the consequences. And the typical application in programming is for performance, like 20% of the execution time your program is spent in 80% of your code. So there's only a few bottlenecks you need to focus on, but that's not our topic. And I think this spirit can apply. I don't know if it's exactly 80% or 90 or 70, I don't know. But I'm sure that all the code is not equal. And that really shows at any scale. Even if you look like at a function, you're going to see that all lines don't matter. There are just a handful of lines that really contain some meaningful action. And I think that's true for like larger scales, like a code base. There are some places where you go everywhere, all the time, Everyone goes there all the time. That's the places that are hot, if I may say, in terms like of cache vocabulary. It's the places that people change. They make fixes because there are bugs or because they are interesting and the clients want more features in them. And those parts, they represent a portion of your code base. And this is the portion that matter. And when you think crudely about it, what is the purpose of having good code? Like, really, we say that good code is a great thing, but why is that? Is it like a good thing with morale? I don't think so. The point of code is to make a piece of software run and to make it run in a way that will make customers happy. And that's a very harsh business view, but I think that's what code is for in a professional context, of course. So making code good has to somehow improve your business. So if you make code better, it can be because better code tends to have less bugs, right? Or because it's easier to add features to better code than it is to code that you can't make any sense of. And that's quite a natural thing to think about. So you need to figure out, where is this code? And that's where you want to focus your efforts. And to think about it, there's this framework I use all the time. I mean, it's very simple things, but that works. It's a value cost analysis. Like, if you want to take an action, it will bring you value. Like, if you want to improve some code, that will bring you value. And that will cost you something. That would cost you mainly time. And time is a finite resource. So every time you want to make a refactoring task, think about how much would it bring and how much would it cost. And when you think this way, some things become obvious. Like, for example, you shouldn't do a refactoring project just because it's easy to do, or just because it doesn't cost a lot. Like, I hear people sometimes say, "Oh, I'm gonna go in that code and improve, I don't know, like the names or make the code cleaner," and that's an easy thing to do, you know. And if no one goes through that code, that doesn't matter. It's the same thing as fixing some other's company code. You know, that won't make you better. That won't make your business better.
Because there's no value. You're saying the cost is low, but the value is zero?
Absolutely. That's exactly my point. Now, I'm not saying that naming is a bad thing. Naming is tremendously important, but that matters more in code that matters.
I assume another concern could be people go into some code that they don't understand. Like, per your definition, they obviously don't understand some aspect of it if it's legacy, and then rewrite it. Like, how do they know that they've actually made it better, or that they haven't introduced new bugs, or etc.?
Right. Well, I think that's two questions. How is it better, and are there new bugs? How is it better in terms of design? Well, I think that ties up well with what we were talking about a bit before, about think about why code is bad, why your piece of code is bad, like being very meticulous in your analysis. I think you can do the same kind of analysis after the fact. Like, when you did choose to fix a piece of code, like to improve its quality by making a refactoring task, after it, I think it's a great thing not to move on immediately, but rather to think about why it's better. And once again, it's not something that's obvious to do sometimes. Like, for example, I remember one time where we had a slightly complicated if statement, like something that was an if involving several booleans and a bit of nesting, you know, nothing monstrous, but, you know, the thing that takes you a few minutes to figure out. And we were thinking, well, this if we see it often, maybe we should do something about it. So we went about and refactored it, and we moved it around, and somehow it was looking much better, much easier to understand. And then we stopped and thought, why is that? Why is it better? You know, it looks better. I feel I can understand it better, and that's the point of code, really. But why is that? And after a few, I don't know, like minutes, perhaps even more, I don't remember, maybe an hour of analysis, or perhaps like when you sleep on it, really, sometimes it comes a few days after, when you do something else in between, we realized it was better because it was sticking to the specification. Like, the business had explained us, if such and such condition are met within this context and without this other, I don't know, special feature, then we should do that thing, And
Mm-hmm.
and after the refactoring, our if statement was looking exactly like that. And surprisingly, it was more nested. By nested, I mean when there's an if statement inside of an if statement, and you can measure nesting with the indentation, which is the distance from the left margin of your screen. And there's general guideline about if statement. That's a classical thing in programming, which is avoid nesting. Like refactor your if statement so that they are as little nested as possible, if can be not nested at all. And in this particular case, the if statement became more nested but clearer, and that was because it stuck better to the specification. So we came up with that guideline that we try to use every time we have to do something that's related to conditional. Try to stick to the specification, to what the business said, more than about nesting. And that's a useful thing to know. So that's for your first question about how do you know it's better. You have to think about it. You have to understand the details, and you can because it's all technical. Now, how do you know if it has more bugs? Well, for one thing, if it's more understandable, it's less likely to have bugs, because the more you understand, the more you will see the bugs. Now, more down to earth thing is tests, really. If you have tests around a piece of code, then you can have more confidence that you didn't break anything, because if you did break something that is covered by your test, then your test will fail and you'll know immediately. So that's something that allows you to move forward tests.
I liked this example, the structural indenting. So following the rule very clearly about reducing indent actually would lead you to a solution that was less good than what you ended up with.
Exactly.
So the rules, it's not totally rule based, but you should be able to explain it somehow.
You have to know that nesting is something that can be dangerous. That's a smell. But performing your analysis on your codes allows you to go further, expand beyond the rules, and that's another level of skills. Do you know what I mean?
Yeah, like you have to have the basics, but then from there, there's more required.
Yeah, right.
In your experience, what percentage of work on legacy code is new features versus bugs and maintenance?
There's this, so I think it depends on projects and companies and people, but the SAFE framework, which is an extension of the Agile methodology, advocates for a 30-70% proportion. So that would be 30% for maintenance and 70% for new features. And people use SAFE with their existing code and legacy code. So I think that's a valid target for legacy code.
And then if we are this junior developer who's new to working in a legacy code base and we need to work on some sort of bug fix for a legacy code base, how would I approach that?
Well, yeah, that's a question that I think every developer has asked or wondered at the beginning of their career. The natural thing to do is to go look at the code, because if there's a bug, then that means that there's something wrong in the code. So you want to go find it. That's basically your mission, and that's actually true. That's true. That's what you want to do. You want to find what's wrong in the code. But surprisingly, the fastest way, or at least the fastest way I know, is not to look at the code. The fastest way I know is, well, start by making sure you can reproduce a problem on your environment, and that's not always a given. And once you do, then you still don't look at the code. You look at the application, and well, there's a step-by-step process that I describe in my book. But the gist of it is that you want to reduce your use case. Like you've got a bug, you got a bug report saying this feature doesn't work properly, and you want to know if it's exactly this feature that has a problem, or perhaps just a subset of it, or perhaps something that's connected with it. So you try and test for other use cases that are close to your initial use case. And at some point, you're going to stop reproducing. And you'll know some sort of the border between the place of the code where you reproduce and the place where you don't reproduce. And that shows a smaller part of the application which is actually concerned with the bug. And once you have this small portion, you can formulate a hypothesis about what is wrong. And only then you can go and open up your debugger and look at the code just to make sure if you got it right just by testing the application. If you got it right, well, awesome. That's you found the cause of the bug. And if you didn't, then you make another hypothesis. And really, that speeds up the code, the analysis so much. I like to compare that with the binary search because that's something that programmers can relate to. You know, when you have to look at something, to look for something in a collection that is sorted, then you have two ways, the slow way and the fast way. The slow way consists in checking the first element, and if it's not the one you're searching for, then you check the second one, and so on. And you're going to check potentially as many elements are there in the collection. And binary search consists in checking right in the middle, and if this is not the one you're looking for, then you see if what you found is smaller or bigger, and accordingly you go left or right, and so on. And you converge in logarithmic time, which is like literally orders of magnitude faster. And I think that's about the same thing with bug finding, because if you look at the code, then you're going to start to read code, and you're going to start to read line by line, hopefully faster with the speed reading techniques we've mentioned and that I detail more in my book. But you're going to have to go through some code. But if you just test out some use cases in the application, it's like locating the place you want to look for, just like you would be locating that place when you do binary search. And that's way faster, for one thing, and that's also way more fun. because you've got this process that works most of the time. I'm not saying it works 100% of the time because you've got like some weird bugs sometimes, but most of the time it works really splendidly. And it's just a matter of time before you find it. So when you do that, your maintenance is a bit like a game, and that's stimulating because it makes you think. And so using your brain is a very motivating thing when you're programming. And yeah, it goes faster and it's more fun.
And why is it important to have a hypothesis?
Because if you don't know what you're looking for. And if you don't know what you're looking for, you're going to look at the code and look for something's wrong, and chances are you're going to find something wrong, but not what's causing your bug. Or you're going to find something that looks wrong and that's not actually wrong and not related. And you're going to go into wrong tracks, and you can go far and waste time in wrong tracks. If you have a hypothesis, on the other hand, you know exactly the answer you want. You have a question, you want an answer, and you ignore everything in the code that's not related to your question.
Yeah, that makes sense. And so you're trying to disprove or prove your hypothesis as you're clicking around. That's the guiding principle.
Precisely.
So do you advise like creating documentation as part of understanding legacy code, or how do we work with a system without documentation, or how do we build up the knowledge?
Yes, what you just said, I think it's an important thing. Documenting helps understanding. Like you can create understanding out of nowhere with documentation. That's a very surprising thing to do, because it sounds like magic. But the very fact of explaining what you already understood helps you understand more. You probably know that if you have made a talk or written a blog post or written a book or written actually a piece of documentation. If you explain anything to anyone in any form, and I'm sure every listener did at some point, you know that this made you realize things. And if anything else, it helped you realize that there were things you didn't know. There were holes in your understanding, and that gives you more questions to answer to make a consistent whole. So that's just one aspect of how documenting helps understanding.
Yeah, that's a great example, because you're saying that the actual act of explaining it to somebody via documentation actually deepens your understanding. It's a way to for you to understand it better.
And of course, it goes without saying that it helps the other people that are going to read your documentation. Now, I think, yeah, when you're a software developer, doing maintenance documentation is not hype. That's not the thing that motivates people becoming developers, or at least most
Yeah.
people I've met. That's why I think it's important to realize how important it is, and that it's not a terrible thing to do. And one way to see things that I've realized over time by actually managing people and making them write documentation is documentation, just like improving code quality. You don't do it because it's a good thing. You know, you don't do it because you're a good person. You do it because it helps the business. And knowing that, you're going to quit this it's horrible for everyone attitude where you write documentation like you would do homework. You know, like my manager asked me to do that. I don't have a choice. I'm going to crank it out and be done with it. And that's the worst documentation you can make for you and for everyone. For you, because it's going to be a pain, and for everyone, because it shows. Really, when you read a piece of documentation that's been written by someone that didn't want to write it, that just cranked it out, it shows. And you don't really understand, and it's not helpful. And if it's not helpful, then you wasted your time, you know?
Yeah, that's a great attitude.
Yeah. So one simple tip I was going to say, when you write documentation, is to write it not because you have to, because you've been asked to, or because you feel guilty not to, but write it to explain something you had a hard time understanding. Explain it to your past self, you know, because you know how it feels not to understand that thing. You know what's easier to understand. You know what's like the tricky parts, and understand it like you are speaking, yeah, to your past self. Because other people are like your past self; they don't know about it, and actually, your future self has a high chance to be like your past self at some point.
Definitely true. So I'm really enjoying your book, Jonathan. One question I had about it was, what made you choose the perspective? So it seems to be written very much from the perspective of, from a practitioner's perspective, somebody who's just been sat down in front of a giant code base and has to work with it. Does that come from your personal experience or?
Yeah, a lot of it does. I've been a software developer for a couple of years now, like 8 years. I, yeah, I've worked my way up. I'm currently a team lead, and I tried to reflect on why I was loving my job and how I progressed since I began. Because when I began, I didn't know anything, pretty much. Had no idea what legacy code was like. I'm not saying that the code I'm working on is terrible. It's I mean, I can't say much about that, but it's not because I had a horror story.
Mm.
Quite the contrary, actually. I noticed that people around me, like the people I met, like at Meetup or on the internet or wherever, they were sad about the code they were working with, and I think it's a terrible thing because most of us, we choose our job out of passion.
Mm.
You know, quite a few developers have been programming before they were actually working as a developer. Legacy code is everywhere, so I was trying to convey to people how to be happy with their job, because it's a fascinating thing to be programming. We love that. So how to be happy and how to make the most of it, how to be efficient, how to be successful, how to get better, how to be happy every day and make fantastic things with your code. And I think this book, I hope this book will change how people see their everyday life with working with existing code.
Well, I think that's a great attitude and also a great place to end. So, where can listeners get your book?
It's available on LeanPub, so you can get it at leanpub.com/legacycode.
And I'll put a link in the show notes. So, Jonathan, thanks for coming on the show.
Thanks for having me.
Yeah, it's been fun. This is Adam Gordon Bell for Software Engineering Radio. Thank you for listening.
Thanks for listening to SE Radio, an educational program brought to you by IEEE Software Magazine. For more about the podcast, including other episodes, visit our website at se-radio.net. To provide feedback, you can comment on each episode on the website or reach us on LinkedIn, Facebook, Twitter, or through our Slack channel at seradio.slack.com. You can also email us at team@se-radio.net. This and all other episodes of SE Radio is licensed under Creative Commons License 2.5. Thanks for listening.